For as long as human beings have looked toward the stars, it has seemed natural to believe that every journey has only one real obstacle: distance. The farther away a destination lies, the longer it takes to reach. Build a faster ship, develop a more powerful engine, and eventually even the most distant world should become accessible by that simple logic. Travelling at the speed of light appears to be nothing more than the next great technological milestone, waiting somewhere beyond our current abilities. Modern physics tells a far stranger story. The speed of light is not merely the fastest speed that light happens to travel, it is woven into the architecture of the universe itself. It is less like the top speed of an exceptionally fast vehicle, and more like the shape of a mountain that no traveller can climb beyond. Every experiment performed over more than a century has pointed toward the same remarkable conclusion. As objects move ever closer to this cosmic limit, nature itself begins to respond in unexpected ways. Time changes, distance changes, energy behaves differently. The closer one approaches this boundary, the more the universe seems determined to prevent it from ever being crossed. At first, this almost feels like a rule invented for convenience, a mathematical restriction placed inside elegant equations. Yet the evidence comes not only from chalkboards and calculations, but from particle accelerators beneath the Earth, from exploding stars billions of light years away, from satellites orbiting our planet, and from the silent arrival of light that has crossed unimaginable stretches of space. Each of these observations tells the same quiet story. The limit is real, but that realization gives rise to a deeper mystery. Why should the universe possess such a limit at all? Why should empty space contain a speed that every observer measures in exactly the same way, regardless of how they themselves are moving? And if nothing carrying mass can ever reach that speed, what is so fundamentally different about light that it alone is allowed to travel there? To answer those questions, we must begin not with distant galaxies or futuristic spacecraft, but with something far more familiar, our everyday understanding of motion itself. Every journey begins with a simple idea of movement. A person walks across a room, a bird crosses the sky, a train glides along its tracks, a spacecraft leaves Earth and slowly disappears into the darkness beyond the moon. Although these examples differ enormously in scale, they all seem to follow the same common principle. Motion appears to be something we can simply add together. If a train is moving forward and someone walks toward the front of the carriage, their speed relative to the ground seems to be the speed of the train plus the speed of their footsteps. This intuitive picture works remarkably well for almost everything humans experience in daily life. For centuries, it was also the foundation of physics. In the 17th century, Isaac Newton described a universe governed by precise mathematical laws. His equations explained the motion of falling apples, orbiting planets, swinging pendulums, and ocean tides with extraordinary accuracy. Within this framework, space was treated as an immense, unchanging stage upon which the events of the cosmos unfolded. Time flowed steadily everywhere, like a universal clock ticking identically for every observer. If two people measured the duration of an event, they should agree. If two observers measured a distance, any differences could be explained simply by perspective. Most importantly, velocities could be added together in exactly the way common sense suggested. For generations, this understanding appeared complete. As telescopes improved, astronomers mapped the motions of planets with increasing precision. Engineers built faster ships and locomotives. Later came automobiles and aircraft. Each new invention seemed to reinforce Newton's elegant description of motion. Even the first rockets launched into space obeyed these familiar principles with astonishing reliability. The universe appeared wonderfully predictable. Yet one phenomenon quietly resisted fitting into this comfortable picture. Light, unlike stones, bullets, or planets. Light refused to behave as though it needed a medium to carry it. Sound requires air, ocean waves require water, vibrations require something to vibrate. It seemed reasonable to 19th century physicists that light, too, must travel through an invisible substance filling all of space. This hypothetical medium became known as the luminiferous ether. The ether was imagined as perfectly transparent and impossible to feel, yet present everywhere. Earth, the sun, and every planet would move through it much as a ship moves through the sea. If this were true, then Earth's motion around the sun should create an ether wind. A beam of light travelling in the direction of Earth's motion ought to move slightly differently from one travelling across it, just as a swimmer moving with a river's current behaves differently from one swimming across the current. The effect would be tiny, but measurable. By the late 19th century, scientific instruments had become precise enough to detect it. The expectation was straightforward. Since Earth travels around the sun at nearly 30 kilometers every second, the speed of light should appear just a little faster in one direction than another, depending on our planet's motion through the ether. Instead, something astonishing happened. No matter how carefully scientists looked, the expected difference refused to appear. Again and again, experiments produced essentially the same answer. Light seemed completely indifferent to Earth's enormous motion through space. At first, researchers suspected experimental errors. The instruments were refined, measurements became even more accurate, new techniques were developed, yet the result remained stubbornly unchanged. The absence of the ether wind was deeply unsettling because it challenged assumptions that had stood for centuries. If Earth was racing through an invisible medium, why could no one detect the motion if velocities always added together? Why did light seem to ignore that rule? These were not merely technical inconveniences. They hinted that the foundations of physics might contain hidden cracks, long before anyone spoke of time dilation or curved spacetime. The mystery announced itself quietly through careful observation. Nature was presenting a result that appeared impossible under the accepted picture of reality. The puzzle grew even more intriguing when another remarkable development emerged. James Clerk Maxwell's equations, formulated in the 1860s, unified electricity and magnetism into a single elegant theory. These equations predicted electromagnetic waves travelling at one specific speed, determined entirely by the electrical and magnetic properties of empty space. That predicted speed matched the measured speed of light almost perfectly. The implication was profound. Light was not merely something moving through space. Light itself was an electromagnetic wave. But Maxwell's equations contained no reference to the motion of the observer. They did not say the speed should change if Earth moved through the ether. They simply produced one universal value. Physicists now faced an uncomfortable contradiction. Newton's mechanics suggested that velocities should combine differently for different observers. Maxwell's equations seemed to insist that light always travelled at exactly the same speed. Both theories had been extraordinarily successful. Both were supported by countless experiments. Yet they could not both be completely correct in their existing forms. For a time, scientists attempted increasingly complicated explanations to preserve the familiar worldview. Some proposed that the ether was somehow dragged along by Earth. Others imagined that matter physically shrank as it moved through the ether, disguising the expected effect. These ideas could explain individual observations, but they lacked simplicity. They felt like repairs applied to an increasingly unstable structure rather than genuine understanding. A deeper answer seemed to be waiting. The familiar universe was beginning to reveal its first inconsistencies. Not because earlier physics had failed, but because it had reached the edge of the everyday world where intuition remained reliable. Beyond that edge, motion itself would have to be understood in an entirely different way. And once that realization took hold, the seemingly impossible behavior of light would become the first clue that space and time were not the fixed background humanity had always assumed them to be. The true revolution had not yet arrived, but the first cracks had already appeared. At first, the contradiction seemed almost too small to matter. The speed of light differed from the speeds encountered in everyday life by an enormous margin. Light travels through empty space at approximately 299,792 kilometers every second. By comparison, Earth races around the Sun at about 30 kilometers per second. While even the fastest aircraft move at only a tiny fraction of that speed, surely whatever strange behavior light exhibited could remain safely confined to such extreme conditions. Yet the deeper physicists examined the problem, the more they realized that it was not about light alone. It was about the very rules used to describe reality. If two trains pass each other on parallel tracks, common sense tells us that each passenger sees the other train moving. Motion is always relative. There is no obvious way to determine which train is really moving and which is really at rest. This principle had been understood since the time of Galileo. A sailor standing below deck on a smoothly sailing ship cannot determine whether the vessel is drifting across the sea or sitting quietly in a harbour simply by observing fish swimming in a bucket or water dripping from a bottle. Every ordinary mechanical experiment gives the same result. Motion, in this sense, is relative. Newton's laws embrace this idea beautifully, but light introduced an unsettling complication. Suppose two spacecraft pass one another in deep space. One shines a flashlight directly ahead. According to everyday reasoning, the second spacecraft should measure the beam's speed as the speed of light plus the speed of the first spacecraft. Yet Maxwell's equations refused to allow that. Every calculation insisted that the light itself must still travel at exactly the same speed. This was not merely unusual, it appeared impossible. Either the centuries-old method of adding velocities was incomplete, or Maxwell's elegant theory of electromagnetism was somehow flawed. Both possibilities were deeply uncomfortable. Scientists searched for subtle corrections that could preserve familiar ideas without overturning them completely. One proposal suggested that objects moving through the ether physically contracted in the direction of motion. If rulers became slightly shorter, while clocks behaved normally, perhaps every measurement would accidentally hide Earth's motion through the ether. This became known as the Lorentz contraction hypothesis. Remarkably, the mathematics worked. Lengths would shrink by precisely the amount needed to explain the puzzling experiments. But the explanation raised a more difficult question. Why should matter mysteriously compress itself simply because it moved through an invisible medium that no one could detect? The hypothesis explained the observations without explaining the underlying reason. It felt less like discovering nature's design and more like placing a carefully fitted patch over an unexplained crack. At nearly the same time, another idea quietly emerged. Perhaps the problem was not with light. Perhaps it was with our assumptions about space and time. This possibility was almost unthinkable. For thousands of years, people had regarded time as universal. A second was a second everywhere. Morning arrived because time flowed forward uniformly throughout the cosmos. Likewise, distance appeared absolute. A meter measured in London should be the same meter measured aboard a ship crossing the Atlantic. These assumptions seemed beyond question because they matched ordinary experience perfectly. But ordinary experience takes place at speeds that are unimaginably slow compared with light. Nature had never forced human intuition to confront the extremes. Simple thought experiments began exposing surprising consequences. Picture two observers standing on a vast railway embankment. A bolt of lightning strikes both ends of a passing train simultaneously. The observer standing beside the track sees both flashes arrive at exactly the same moment and concludes the strikes occurred simultaneously. Now consider a passenger seated exactly in the middle of the moving train. While the light from each lightning strike travels toward the passenger, the train itself continues moving. The passenger moves toward the light coming from the front strike and away from the light coming from the rear strike. If light always travels at the same speed regardless of the observer's motion, the passenger receives the two flashes at different times. One arrives first, the other arrives later. Both observers are perfectly correct according to the measurements available to them. Yet they disagree about something that had always seemed objective. They disagree about whether two events happen simultaneously. This was an astonishing conclusion. It suggested that simultaneity itself was not universal. Two events that occur at the same moment for one observer need not occur at the same moment for another moving observer. The implication reached much further than lightning strikes. If observers could disagree about when events occurred, then time itself could no longer be an independent background against which the universe unfolded. Time depended upon motion. This idea sounded almost philosophical, yet it emerged directly from the simple requirement that every observer measure the same speed of light. No exotic particles were required. No mysterious forces, only careful logic. As physicists explored these consequences further, one surprising prediction followed another. Moving clocks should tick more slowly than stationary ones. Fast-moving objects should become shorter along their direction of travel. Massive amounts of energy would be required for even modest increases in speed near light's limit. None of these ideas resembled everyday experience, yet all flowed naturally from the same underlying principle. Perhaps most unsettling of all was the realization that cause and effect themselves depended upon this cosmic speed limit. If information could travel faster than light, one observer might witness an effect before another observer had seen its cause. The orderly sequence of events upon which science depends could begin to unravel. The speed of light was no longer merely the speed of an electromagnetic wave. It appeared to protect the logical structure of reality itself. Still, these conclusions remained almost entirely theoretical. Elegant mathematics can sometimes lead physicists astray. Extraordinary predictions require extraordinary evidence. No one had yet directly observed clocks slowing because of motion. No one had measured shrinking rulers aboard rapidly moving spacecraft. The strange consequences remained hidden, because human technology had not yet reached speeds where they became obvious. The cracks in classical physics had widened dramatically, but they had not yet forced the old structure to collapse. That transformation would come through the work of a young patent examiner who dared to ask an extraordinarily simple question. What if every observer really did measure exactly the same speed of light? Rather than trying to explain away that possibility, he chose to accept it completely. The consequences would reshape physics forever. In the early years of the 20th century, physics stood in a curious position. On one hand, it had never been more successful. Newton's laws described the motions of planets with extraordinary precision. Maxwell's equations explained electricity, magnetism, and light with remarkable elegance. Engineers were transforming the world with steam engines, telegraphs, electric power, and the first automobiles. To many scientists, it seemed that only a handful of minor problems remained before physics would be essentially complete. Yet hidden beneath this confidence was a growing unease. Experiments refused to reveal the Earth's motion through the ether. Maxwell's equations demanded that light travel at a fixed speed. Newtonian mechanics insisted that speeds should add together. These ideas could not all be true in their existing forms. Many physicists attempted to repair the contradiction by adding increasingly sophisticated mathematical corrections. They imagined invisible substances, contracting objects, and subtle mechanical effects. Each solution addressed one difficulty while creating another. Then, in 1905, a very different approach appeared. The author was not the head of a famous observatory or the director of a prestigious laboratory. He was a 26-year-old patent examiner in Bern, Switzerland. His daily work involved reviewing technical inventions submitted by engineers and inventors. The position required unusual clarity of thought. Every design had to be understood from first principles. Assumptions had to be questioned. Unnecessary complications had to be stripped away until only the essential mechanism remained. His name was Albert Einstein. Instead of asking how light could fit into the existing picture of space and time, Einstein asked a simpler question. What if the existing picture itself was wrong? His insight did not emerge from a new telescope or a powerful experiment. It came from carefully following two ideas that already seemed well established. The first was the principle of relativity inherited from Galileo. The laws of physics should be the same for every observer moving at a constant speed. No smooth, constant motion should allow someone to determine whether they were truly at rest. The second was suggested by Maxwell's equations and supported by experiment. The speed of a light in a vacuum appeared to be the same for every observer, regardless of the motion of the source. Most physicists accepted the first idea. Many accepted the second. Almost no one believed they could both be true simultaneously. Einstein did. Rather than modifying one principle to save the other, he accepted both completely and allowed logic to reveal the consequences. The results were astonishing. If every observer measures the same speed of light, then something else must change instead. Space, time, or both. The conclusion was unavoidable. Length cannot remain absolute. Time cannot flow identically for everyone. Events that appear simultaneous to one observer cannot always be simultaneous to another. These were not separate effects. They were different expressions of a deeper reality. Space and time were woven together. Today, physicists speak of space-time as though it were an ordinary concept. But in 1905, this represented a profound shift in humanity's understanding of the universe. For thousands of years, People had imagined space as a vast container and time as an invisible river flowing independently through it. Einstein's work suggested that the two could no longer be separated. They formed a single fabric. Motion through one affected the experience of the other. One of the simplest ways to glimpse this new picture is through what has become known as the light clock. Imagine a clock built from two perfectly parallel mirrors. A pulse of light bounces between them. Each round trip marks one tick. If the clock rests on a table, the light travels straight up and down between the mirrors. Now imagine placing that same clock aboard a spacecraft moving at tremendous speed. To someone inside the spacecraft, nothing changes. The light still travels directly between the mirrors. The clock ticks normally, but an observer watching from outside sees something different. As the spacecraft moves forward, the light no longer follows a simple vertical path. Instead, it traces a diagonal zigzag, travelling a longer distance between each tick. Yet both observers agree that light itself always moves at exactly the same speed. If the light covers a greater distance without moving faster, only one conclusion remains. Each tick of the moving clock must take longer. The clock runs more slowly. Nothing inside the spacecraft appears unusual to its passengers. Their hearts beat normally. Their conversations continue naturally. Every biological process proceeds exactly as expected. It is only when compared with another observer moving differently that the difference becomes apparent. Time itself depends upon the observer's motion. This phenomenon became known as time dilation. It sounds almost impossible until one remembers that every measurement of time ultimately relies upon some repeating physical process. Whether it is a pendulum swinging, atoms vibrating, or light bouncing between mirrors, a clock is simply matter following the laws of physics. If those laws require moving clocks to tick differently, then time itself cannot be independent of motion. Length changes in a similar way. To preserve the constant speed of light, distances measured along the direction of motion become shorter for moving objects. This effect, known as length contraction, is imperceptible at ordinary speeds. Even modern airliners move far too slowly for passengers to notice any measurable difference. Only when approaching a significant fraction of light speed do these distortions become substantial. The remarkable feature of Einstein's theory was not merely that it predicted strange effects, it predicted them with extraordinary precision. Every equation followed naturally from the two simple principles with which he began. No invisible ether was required, no mysterious mechanical contractions imposed from outside. The geometry of space-time itself explained everything. At first, many physicists found these conclusions deeply unsettling. The ideas contradicted centuries of intuition. Even Einstein reportedly described some of the consequences as difficult to accept emotionally despite recognizing their logical necessity. Science, however, is not guided by comfort. It is guided by observation. Over the decades that followed, experiment after experiment confirmed the predictions. Atomic clocks flown aboard aircraft accumulated tiny differences exactly matching relativity. Fast-moving particles created high in Earth's atmosphere survived far longer than classical physics predicted because, from our perspective, their internal clocks were running more slowly. The global positioning system, used daily by billions of people, must account for both special and general relativistic effects. Without those corrections, navigation errors would grow by several kilometers each day. Relativity is no longer an abstract theory discussed only in university lecture halls. It quietly governs technologies woven into everyday life. Yet even these remarkable discoveries revealed only part of the story. Einstein had shown why space and time behave differently near the speed of light. He had explained why clocks slow and distances shrink. But another question soon emerged. If moving ever faster changes the fabric of space and time themselves, what happens as an object approaches the speed of light? Does the journey simply continue? Or does nature impose an even deeper limit that no amount of engineering can overcome? The answer would prove even more extraordinary than the revolution that revealed space-time itself. By the beginning of the 20th century, Einstein's theory of special relativity had transformed the way physicists thought about motion. Space and time were no longer fixed backgrounds. They were flexible, interconnected, and dependent upon the observer. Yet the most surprising consequence of the theory did not concern clocks or rulers. It concerned energy. For centuries, motion had seemed wonderfully straightforward. Push an object with a constant force, and it accelerates. Continue pushing, and it continues to gain speed. A stronger engine simply produces a faster vehicle. This expectation remains almost perfectly true in everyday life. A cyclist pedals harder and accelerates. An aircraft increases its thrust and flies faster. A rocket fires its engines and steadily gains velocity as it climbs away from Earth. Nothing in ordinary experience suggests that nature would suddenly become reluctant to allow further acceleration, but relativity quietly changes the rules, at very low speeds. The difference is so small that Newton's equations remain an excellent approximation. Even the fastest spacecraft humanity has ever built travel at only a tiny fraction of light speed. Their behavior is described accurately enough by classical mechanics. The deeper effects remain hidden. Only when velocities become an appreciable fraction of the speed of light does the universe begin to reveal a different character. To understand why, it helps to think not about reaching the finish line, but about climbing a mountain. Near the base, every step carries you noticeably higher. The effort feels manageable, and progress is obvious as the slope becomes steeper. However, each additional meter demands more energy than the last. Eventually, the climb becomes so demanding that enormous effort produces only modest gains. Approaching the speed of light resembles this kind of ascent. At first, increasing speed is relatively easy, then each improvement becomes progressively more expensive. Not because the engine has weakened, not because friction has appeared in empty space, but because space-time itself responds differently as velocities approach its fundamental limit. This behavior becomes clear in one of the most famous relationships in all of science, Einstein's equation. E is often introduced as a statement that mass can be converted into energy. That is certainly true. Nuclear reactions inside stars and reactors demonstrate this remarkable equivalence every moment. But the equation carries a broader meaning. Mass and energy are not separate substances. They are different expressions of the same physical reality. A stationary object already possesses an enormous amount of energy simply because it has mass. As an object accelerates, additional energy is supplied. Unlike classical physics, however, that extra energy does not translate into speed with the same efficiency forever. Instead, more and more of the added energy contributes to the object's increasing relativistic energy, while producing progressively smaller increases in velocity. The closer the object comes to light speed, the less each new unit of energy changes its speed. This is one reason physicists today usually avoid saying that an object's mass literally increases with velocity, a description common in older textbooks. Modern treatments instead emphasize that the object's invariant mass remains constant while its total energy and momentum grow dramatically. The distinction is subtle but important. The physical prediction remains the same. As velocity approaches the speed of light, the required energy rises without bound. The consequences become easier to appreciate through an example. Suppose a spacecraft could somehow accelerate continuously through deep space, free from the pull of planets or stars. During the early stages of the journey, each burst of engine power would noticeably increase its speed. Weeks later, it might be traveling at 10% of light speed, with continued acceleration, perhaps 50%. Eventually, 90%, even 99%. Each milestone represents an extraordinary achievement, yet the remaining gap grows increasingly stubborn. The difference between 99% and 99.9% of light speed appears numerically small. In reality, it demands vastly more energy. Reaching 99 to a steady percent requires dramatically more still. Each additional decimal place becomes harder than all the previous ones combined. The destination recedes even as the spacecraft continues accelerating. This is not merely a limitation of present-day technology. It emerges directly from the mathematical structure of relativity. No engine design changes the underlying geometry. No improvement in fuel efficiency removes the barrier. As long as the object possesses mass, the energy required to reach exactly the speed of light becomes infinite. Infinite energy is not simply a very large number. It is something fundamentally unattainable within the known laws of physics. This realization profoundly reshapes how engineers and physicists think about interstellar travel. The challenge is not merely building larger rockets. Chemical propulsion, nuclear fusion, antimatter engines, laser sails. or concepts yet to be invented may all achieve astonishing velocities compared with today's spacecraft. Some theoretical designs could, in principle, approach a substantial fraction of light speed, yet none avoid the underlying relativistic cost. Better technology can move humanity closer to the limit. It cannot erase the limit itself. Nature imposes the same rule upon everything. Remarkably, the universe provides laboratories where these ideas are tested every day. Deep beneath the borders of France and Switzerland lies the Large Hadron Collider, the most powerful particle accelerator ever constructed. Inside its circular tunnel, protons are accelerated until they travel at more than 99.99% of the speed of light. Their speed is astonishingly close to the cosmic limit, yet despite the enormous energy added by powerful superconducting magnets and radio frequency cavities, the particles never exceed the speed of light. Instead, the extra energy continues increasing their momentum and total energy, while their speed changes by only tiny amounts. The accelerator is not failing. It is behaving exactly as Einstein's theory predicts. Nature refuses to allow the final step. Cosmic rays offer another demonstration. Some particles arriving from distant astrophysical events carry energies millions of times greater than those produced by human accelerators. They have travelled across galaxies after being accelerated near exploding stars, rapidly spinning neutron stars, or the environment surrounding supermassive black holes. Even these extraordinary particles, among the most energetic ever observed, remain just below the speed of light. Again and again, across vastly different environments, the same limit appears. This consistency is one of the strongest reasons physicists regard the speed limit as a fundamental property of the universe, rather than an engineering inconvenience. Yet relativity introduces another remarkable twist. While outside observers see the spacecraft struggling ever harder to gain additional speed, the travellers aboard experience something very different. Their clocks tick more slowly relative to Earth. Distances in the direction of travel become shorter. To them, the destination itself begins to draw nearer. A voyage that appears to require thousands of years from Earth's perspective might occupy only decades for those making the journey. This does not violate relativity. Both descriptions are correct within their respective frames of reference. The universe allows the travellers to cross immense distances within their own lifetime. What it does not allow is reaching or exceeding the speed of light itself. This subtle distinction has inspired generations of scientists, engineers, and storytellers alike. If time and distance can transform so dramatically, perhaps the light speed barrier is not as absolute as it first appears. Or perhaps its true significance lies even deeper than energy alone. For beneath every calculation remains an unresolved question. Why should possessing mass make such a profound difference? Why can light move effortlessly at this ultimate speed while every object built from matter is forever denied it? That mystery leads directly to the heart of the cosmic limit itself. The closer physicists examined the speed of light, the more it began to resemble something unlike any ordinary limit found in nature. A mountain has a highest peak because of the way rock and gravity shape the landscape. An aircraft has a maximum speed because its engines can produce only so much thrust before air resistance overwhelms them. A rocket eventually runs out of fuel because its tanks are finite. These are practical limits. Build a stronger engine, a lighter airframe, or carry more fuel and the limit changes. The speed of light is different. No stronger engine changes it. No improved material alters it. No more efficient source of energy moves it even slightly. It is a limit that belongs not to machines, but to the fabric of reality itself. This distinction is essential. When people ask why humans cannot travel at the speed of light, they often imagine a technological obstacle. Perhaps future civilizations will simply construct more powerful spacecraft. Perhaps one day an engine will be invented that overcomes today's shortcomings. Physics offers a much deeper answer. The obstacle is not the spacecraft. It is the traveller. Anything with mass enters spacetime under rules fundamentally different from those governing light itself. To understand why, we first need to ask a deceptively simple question. What is mass? In everyday life, mass is often described as the amount of matter contained within an object. That description is useful, but incomplete. In modern physics, mass is more deeply connected to inertia. Inertia is the tendency of an object to resist changes in its motion. Push a tennis ball, and it accelerates easily. Push a freight train with the same force, and almost nothing happens. The train possesses greater inertia. Its mass measures how strongly it resists acceleration. At ordinary speeds, this idea seems entirely straightforward. Double the force, and acceleration roughly doubles. Double the mass, and acceleration is roughly halved. Newton's laws describe this beautifully, but relativity quietly modifies the picture as velocity increases, as an object approaches the speed of light. Its momentum grows far more rapidly than Newton's equations predict. Each additional increase in speed demands disproportionately more energy, not because the object's mass is changing in the everyday sense, but because spacetime itself links energy, momentum, and velocity in a different way than classical mechanics allows. The mathematics reveals something remarkable. For any object with non-zero rest mass, there is simply no finite amount of energy capable of carrying it to exactly the speed of light. The required energy does not merely become impractically large, it diverges without limit. This is the heart of the mystery. It is not that the universe refuses after a certain point because of some hidden mechanical barrier. The equations themselves contain no pathway beyond the limit. It is as though every possible route through space-time bends away before the destination can ever be reached. Curiously, light faces no such difficulty. Photons, the particles associated with light, possess no rest mass. That single fact changes everything. Unlike atoms, planets, spacecraft, or human beings, photons are never observed sitting still. There is no meaningful experiment in which a photon can be brought to rest and then accelerated. From the moment it exists until the moment it is absorbed, it travels through the vacuum at the invariant speed we call the speed of light. This often leads to a common misconception. People sometimes ask why photons are allowed to travel at light speed while everything else is forbidden. The better way to think about it is that photons are not accelerating up to that speed. They simply exist in a category of particles whose behavior is fundamentally different from particles with mass. Massive particles occupy one class of possible paths through space-time. Massless particles occupy another. Relativity does not treat them differently out of preference. It treats them differently because their very nature is different. One helpful way to picture this comes from the geometry physicists use to describe space-time. Although the mathematics is sophisticated, the underlying idea is surprisingly elegant. Every event in the universe can be represented as a point in space-time. From each point extends what physicists call a light cone. The light cone marks every direction that light could travel away from that event. Anything moving more slowly than light must remain inside this cone. Nothing carrying information or possessing mass has ever been observed leaving it. The cone is not a physical object. It is a map of what cause and effect allow. If something could travel faster than light, it would move outside the light cone. The consequences would be extraordinary in some reference frames. An observer could receive information before another observer had sent it. Cause and effect could become reversed. An answer might arrive before the question had been asked. The familiar sequence of past, present, and future would lose its universal ordering. This possibility is one reason physicists believe the speed of light is tied not merely to motion, but to causality itself. Causality is one of the deepest principles in science. Every experiment assumes that causes precede effects. Stars form before they explode. A stone is thrown before it strikes the ground. Signals are transmitted before they are received. Without this ordering, the logical foundation of physics would begin to collapse. Relativity preserves that ordering through the light speed limit. The cosmic speed limit is therefore not only about transportation. It protects the structure of time itself. This realization transformed the question scientists were asking. Instead of wondering how to build a faster spacecraft, they began asking why space-time possesses precisely this causal structure. Why should the maximum speed be approximately 299,792 kilometers per second rather than any other value? Could the universe have been different? Would atoms remain stable? Would stars still shine? Would galaxies even form? These questions lead far beyond engineering. They touch the deepest relationships between matter, energy, electromagnetism, and space-time. Modern theories suggest that the speed of light is not an arbitrary number chosen by nature. It emerges from fundamental properties of the vacuum itself. Maxwell's equations relate the speed of electromagnetic waves to two measurable quantities, the electric permittivity and magnetic permeability of empty space. Together, these constants determine the value of the speed of light. This discovery hints that empty space is not truly empty. It possesses measurable physical properties. The vacuum behaves almost like a medium, though not in the old 19th century sense of the ether. Instead, according to quantum field theory, what we call empty space is filled with fluctuating quantum fields whose lowest energy state still possesses structure. Particles can briefly appear and disappear through quantum fluctuations. Fields extend throughout the entire universe. Matter itself arises as localized excitations of these fields. The vacuum is not a void. It is the stage from which everything else emerges. Could the speed of light ultimately arise from this deeper quantum structure? Physicists do not yet know. Some approaches to quantum gravity suggest that spacetime itself may have an underlying microscopic architecture unlike anything described by classical relativity. Others predict that the speed of light remains exactly constant even at the smallest imaginable scales. So far, every observation supports Einstein's picture with astonishing precision. No confirmed experiment has revealed a violation, and yet the mystery remains. Relativity explains how the light-speed barrier behaves. It explains what happens as massive objects approach it. It explains why photons occupy a different category. But explaining the rules is not quite the same as explaining why those rules exist. That unanswered why has become one of the most profound questions in modern physics. To explore it further, scientists have turned away from thought experiments alone. Instead, they have searched the universe itself, allowing nature to perform experiments on scales no laboratory could ever reproduce. What they have found has only strengthened the mystery. A scientific theory becomes truly powerful only when it survives contact with nature. Elegant mathematics can inspire new ways of thinking, but equations alone are never enough. The universe has the final word. Every prediction must eventually face observation, measurement, and experiment. Special relativity has faced that test for more than a century. Again and again, the evidence has pointed in the same direction, not because scientists expected it to, but because nature consistently behaves as though the speed of light is woven into its deeper structure. Some of the clearest evidence comes from places that seem almost ordinary. High above Earth's surface, cosmic rays constantly strike the upper atmosphere. These particles, accelerated by violent events throughout the Milky Way and beyond, collide with atoms in the air and produce showers of short-lived particles. Among them are particles called muons. A muon is similar to an electron but around 200 times more massive, unlike electrons. However, muons are unstable, left undisturbed. An average muon survives for only about 2.2 millionths of a second before decaying into other particles. At first glance, this seems unremarkable, yet it creates a fascinating puzzle. Muons are typically produced more than 10 kilometers above Earth's surface, even moving close to the speed of light. A particle living for only a few microseconds should travel only a few hundred meters before disappearing. Most should decay long before reaching the ground, and yet they do, every second. Muons pass harmlessly through our bodies, through buildings, through mountains, and into detectors beneath the Earth's surface. For decades, physicists wondered how this could be possible. The answer turned out not to be hidden in the muons themselves. It was hidden in time. From our perspective on Earth, the muons are moving at enormous speeds. According to special relativity, their internal clocks run more slowly than clocks at rest beside us. To the muons, their lifetime has not changed. They still exist for about 2.2 microseconds according to their own clocks. But from our perspective, those microseconds stretch into a much longer interval. The particles simply have more time to complete their journey. The remarkable feature of this explanation is that it was not invented afterward to match the observations. The amount of time dilation follows directly from Einstein's equations. When scientists calculate how many muons should survive the trip to Earth's surface using relativity, the predicted number agrees closely with what detectors actually measure. Without relativity, the observations make little sense. With relativity, they become expected. The universe behaves exactly as though moving clocks truly tick more slowly. Particle accelerators provide another opportunity to test these ideas under carefully controlled conditions, unlike cosmic rays, which arrive unpredictably from distant astrophysical sources. Accelerators allow scientists to prepare particles with precisely known energies and observe their behavior in extraordinary detail. Inside facilities such as the Large Hadron Collider near Geneva, protons race around a circular tunnel nearly 27 kilometers in circumference. Powerful superconducting magnets keep the particles on course, while radio frequency cavities continuously increase their energy. Eventually, the protons travel at more than 99% of the speed of light. To human intuition, there seems almost no room left for improvement, yet engineers continue supplying additional energy. What happens? The particles do not suddenly break the light speed barrier. They do not even come noticeably closer in terms of velocity. Instead, the added energy primarily increases their momentum. The speed changes only by unimaginably tiny amounts. This behavior initially surprises many students of physics. One might expect enormous machines delivering enormous amounts of energy to produce dramatic increases in speed. Instead, nature quietly insists that the extra energy goes elsewhere, exactly where Einstein's theory predicts. The closer the particles approach the speed of light, the more reluctant spacetime becomes to grant further increases in velocity. The accelerator is not revealing a technological shortcoming. It is revealing one of the fundamental rules of reality. Evidence also arrives from much farther away. Across the universe, exploding stars, rapidly rotating neutron stars, and supermassive black holes accelerate particles to energies vastly beyond anything humanity can currently produce. These natural accelerators generate cosmic rays carrying astonishing amounts of energy. Some individual particles possess energies comparable to those of a well-hit baseball, concentrated into a single atomic nucleus. That comparison sounds almost unbelievable, until one remembers how unimaginably small a nucleus is. If any known process could propel matter beyond the speed of light, such extreme environments would seem excellent candidates. Yet no observation has ever confirmed such an event. Even the highest energy cosmic rays detected remain consistent with relativity. They approach the limit extraordinarily closely. They do not cross it. Light itself provides another series of natural experiments. When astronomers observe distant galaxies billions of light-years away, they are seeing light that began its journey long before the Earth existed in its present form. Some photons have traveled across expanding space for more than 13 billion years. During that immense journey, they pass through magnetic fields, intergalactic plasma, gravitational wells, and the expanding fabric of the cosmos itself. Despite this extraordinary voyage, the measured behavior of light remains astonishingly consistent. Its speed in a vacuum appears unchanged. If the fundamental speed limit varied significantly across space or time, astronomers would expect subtle distortions in the arrival times of different wavelengths or energies. Modern observations have searched carefully for such effects. Within current experimental precision, none have been confirmed. Gravitational waves have added another remarkable line of evidence. For centuries, gravity was understood only through its influence on matter. Then, in 2015, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO, directly detected ripples traveling through spacetime itself. These waves had been generated by two merging black holes more than 1 billion light-years away. Subsequent observations became even more revealing. In 2017, astronomers observed both gravitational waves and ordinary light from the collision of two neutron stars. The signals had travelled across the cosmos for roughly 130 million years. Despite that unimaginable journey, they arrived at Earth separated by only a very short interval, largely attributable to the complex physics of the collision itself rather than differences in propagation speed. The observation placed extraordinarily tight limits on any possible difference between the speed of gravitational waves and the speed of light. Once again, nature appeared to respect the same fundamental structure predicted by relativity. Evidence has also come from technologies so familiar that most people rarely think about the physics operating behind them. Every smartphone that determines its location through satellite navigation depends upon exquisitely accurate timing. The satellites carrying atomic clocks orbit Earth at high speed, while also experiencing weaker gravity than clocks on the ground. Both effects alter the rate at which time passes. Special relativity causes the moving satellite clocks to tick slightly more slowly. General relativity causes the weaker gravitational field to make them tick slightly faster. Engineers must account for both. Without these corrections, navigation errors would accumulate by several kilometers every day. Every successful position calculated by a navigation receiver quietly confirms Einstein's understanding of spacetime. Perhaps the most impressive aspect of all this evidence is its diversity. Particle accelerators, cosmic rays, atomic clocks, satellite navigation, supernovae, neutron stars, gravitational wave observatories. None of these systems were designed merely to test the speed of light, yet each one, operating in entirely different environments and across vastly different scales, tells the same story. The agreement is so broad that physicists now regard the invariant speed of light as one of the best tested principles in all of science. Still, careful scientists remain cautious. Agreement with existing experiments does not prove that a theory is absolutely complete. History reminds us that every successful theory has limits. Newton's mechanics works beautifully until velocities become extreme. Relativity itself may eventually require refinement when combined with quantum gravity. The evidence tells us what nature has revealed so far. It does not guarantee that deeper layers remain undiscovered. That possibility keeps the search alive. If the speed of light truly defines the structure of space-time, every future experiment should continue to support Einstein's picture. But if hidden physics waits beyond our current reach, perhaps tiny deviations will someday appear. The challenge is that any such deviation must be extraordinarily subtle, because the evidence accumulated over the past century leaves remarkably little room for error. It is precisely this tension between overwhelming confirmation and the possibility of deeper truth that has inspired physicists to explore ideas once considered almost impossible. Some remain firmly within established theory. Others venture into the realm of bold hypothesis. The next step is to examine those competing ideas carefully, separating observation from speculation, and asking whether any path around the cosmic speed limit might truly exist. The history of science is filled with ideas that once seemed impossible. Continents were thought to be fixed until evidence revealed that they drift across Earth's surface. Invisible atoms became accepted only after countless experiments confirmed their existence. Even black holes, first emerging as mathematical solutions to Einstein's equations, were regarded by many physicists as curious abstractions before decades of observation established them as real, astronomical objects. Because of this history, scientists are naturally cautious about dismissing unfamiliar ideas too quickly. At the same time, caution works in both directions. An idea is not accepted because it is imaginative. It must also survive careful mathematical analysis and experimental testing. Nowhere is that balance more important than in the search for ways around the light speed limit. Over the past century, physicists have proposed many possibilities. Some arise naturally from established mathematics. Others remain highly speculative. Some have already been ruled out by observation. Others continue to be explored because existing evidence has not yet excluded them. The challenge is distinguishing between what has been observed, what is theoretically possible, and what remains little more than an intriguing suggestion. One of the oldest ideas involves particles known as tachyons. The name comes from the Greek word tachys, meaning swift. Unlike ordinary matter, tachyons were proposed as hypothetical particles that would always travel faster than light. Curiously, according to the mathematics in which they first appeared, a tachyon could never slow down to the speed of light, just as ordinary matter can never speed up to reach it. The light-speed boundary would separate two entirely different classes of particles. This possibility fascinated physicists because it seemed to preserve the symmetry of relativity. Massive particles would forever remain below the limit. Massless particles such as photons would move exactly at the limit. Tachyons, if they existed, would remain forever above it. But fascination is not evidence. Despite decades of experimental searches, no confirmed tachyon has ever been observed. More importantly, faster-than-light particles create serious problems for causality. Depending on the observer's frame of reference, information carried by tachyons could appear to arrive before it was sent. Messages could, in principle, travel backward through time. Such paradoxes do not automatically prove tachyons impossible, but they suggest that any consistent theory containing them would require a much deeper understanding of space-time than physicists currently possess. Today, tachyons occupy an unusual position. They remain mathematically interesting in certain theoretical contexts, but there is no experimental evidence that they exist as real particles travelling through space. The distinction is important. They belong to the category of hypothesis, not observation. Another idea has captured the imagination of scientists and the public alike: the warp drive, unlike tachyons. The warp drive does not propose accelerating a spacecraft beyond light speed. Instead, it attempts to change the geometry of spacetime itself. In 1994, the Mexican theoretical physicist Miguel Alcubierre discovered an intriguing mathematical solution to Einstein's field equations. His proposal described a region of spacetime in which space ahead of a spacecraft contracts, while space behind it expands. The spacecraft itself remains inside a small bubble of relatively undisturbed spacetime. Within that bubble, the ship never locally exceeds the speed of light. Instead, spacetime carries it along. A useful analogy is a moving walkway at an airport. A person standing on the walkway never needs to sprint faster than everyone else. The walkway itself transports them. In the Alcubierre concept, spacetime becomes the moving walkway. At first glance, the idea appears to bypass relativity rather than violate it. General relativity already allows space itself to expand. Indeed, the expansion of the universe causes distant galaxies to recede from one another at effective speeds that can exceed the speed of light without breaking special relativity, because it is space itself stretching rather than galaxies racing through space. This makes the warp drive mathematically intriguing. Yet serious obstacles remain. The original Alcubierre solution requires forms of matter with negative energy density. In quantum physics, certain effects, such as the Casimir effect, can produce extremely small regions where energy behaves in unusual ways. However, nothing remotely resembling the enormous amounts of negative energy required for a practical warp drive has ever been observed. Even optimistic revisions reduce the energy requirements without eliminating the fundamental challenge. At present, no known technology can produce or control such conditions. The warp drive therefore occupies a different category from tachyons. It is based on genuine solutions within general relativity, but whether nature actually permits the required conditions remains unknown. It is an accepted mathematical possibility. It is not an accepted physical reality. Closely related to the warp drive is another concept rooted in Einstein's theory: the wormhole. A wormhole is a hypothetical shortcut connecting two distant regions of space-time. Rather than crossing the enormous distance between stars, a traveller would pass through a tunnel linking the two locations. To outside observers, the journey might appear almost instantaneous. The idea emerged naturally from solutions to Einstein's equations and has been explored extensively in theoretical physics. Some wormhole models even suggest that the entrances could exist at different points in time as well as space, leading once again to profound questions about causality. But here too, significant difficulties arise. Known solutions generally require exotic matter capable of preventing the tunnel from collapsing under its own gravity. No naturally occurring traversable wormhole has ever been observed. Black holes, despite frequent appearances in science fiction, are not known to function as usable wormholes. The mathematics describing their interiors remains incomplete, especially where quantum gravity becomes important. Astronomers have discovered many black holes. They have not discovered a traversable shortcut through space-time. Another proposal occasionally appears in discussions of faster-than-light travel: quantum entanglement, when two particles become entangled. Measurements performed on one are correlated with measurements performed on the other, even if the particles are separated by enormous distances. Albert Einstein famously referred to this phenomenon as spooky action at a distance. At first glance, entanglement seems to allow instantaneous communication, yet decades of careful experiments have shown something subtler. The correlations appear immediately, but they cannot be used to transmit usable information faster than light. Observers comparing their measurements must still exchange ordinary information limited by the speed of light. Entanglement challenges classical intuition. It does not provide a faster-than-light telephone, Modern quantum theory remains fully consistent with relativity on this point. There are also speculative ideas suggesting that relativity itself might break down at unimaginably high energies near the Planck scale, where quantum gravity becomes important. Some approaches to quantum gravity propose that spacetime may possess a discrete microscopic structure rather than being perfectly smooth. Others suggest that Lorentz symmetry, one of the central principles underlying special relativity, could be modified under extreme conditions. If such effects exist, they would almost certainly be incredibly small. Astronomers have searched for them by studying gamma-ray bursts, distant quasars, ultra-high-energy cosmic rays, and other extreme phenomena. So far, no convincing violation has been confirmed. Einstein's framework continues to pass every observational test. This brings us to an important distinction that often becomes blurred outside scientific discussions. Facts are observations directly supported by measurement. Evidence consists of observations interpreted through careful analysis. Accepted theories are explanatory frameworks repeatedly confirmed across many independent experiments. Hypotheses are proposed explanations that remain under investigation. Speculation extends beyond available evidence while remaining logically consistent with known physics, or sometimes deliberately exploring possibilities that known physics does not yet support. Keeping these categories separate is one of science's greatest strengths. It allows curiosity to flourish without allowing imagination to replace evidence. At present, the facts are remarkably clear. No object with mass has ever been observed travelling at or above the speed of light. Special and general relativity have been confirmed across an extraordinary range of experiments. Warp drives and traversable wormholes remain mathematically interesting but physically unverified. Tachyons remain hypothetical. Quantum entanglement does not enable faster-than-light communication. Quantum gravity may eventually deepen our understanding. But no experiment has yet demonstrated that the light speed limit is violated. This does not mean exploration should stop. Quite the opposite. Many of history's greatest discoveries began by carefully examining ideas that initially seemed unlikely. The difference is that science advances not by believing extraordinary possibilities, but by testing them relentlessly among these competing ideas. One possibility stands apart because it asks a particularly revealing question. Suppose, just for the sake of careful reasoning, that humanity somehow found a way to overcome the light speed barrier. Not because the evidence says we can, but because following that thought experiment may reveal why the barrier exists in the first place. Thought experiments have occupied a special place in physics for centuries. Unlike ordinary experiments, they require no laboratory, no telescope, and no particle accelerator. They begin with a carefully chosen assumption and follow its consequences wherever logic leads. When used responsibly, they can reveal hidden contradictions, expose overlooked principles, or illuminate ideas that are difficult to observe directly. Albert Einstein relied on thought experiments throughout his career, long before technologies existed to test many of his predictions. He imagined riding alongside a beam of light, watching clocks on moving trains, or observing elevators drifting through empty space. These simple mental pictures helped uncover some of the deepest structures of modern physics. Following that tradition, let us ask a question that physics itself does not currently answer in the affirmative. Suppose a human spacecraft could somehow reach the speed of light. Not 99.999%, not so close that no ordinary instrument could distinguish the difference. Exactly the speed of light. The first consequence appears surprisingly simple. From the viewpoint of ordinary relativity, there is no valid reference frame in which a massive object can be at rest while simultaneously moving at light speed. This statement is more subtle than it first appears when sitting inside an aircraft. Passengers naturally regard themselves as stationary. The Earth seems to move beneath them. Likewise, astronauts floating inside an orbiting spacecraft experience themselves as being at rest. Physics allows every observer moving at constant velocity to consider themselves stationary within their own frame of reference. But this familiar idea breaks down at light speed. The mathematical transformations that relate one observer's measurements to another become undefined for a massive object travelling exactly at the speed of light. In effect, relativity refuses to construct such a frame. It is not merely difficult. Within the existing theory, it has no meaning. That mathematical failure hints that something deeper is at stake. Now consider the flow of time. Earlier in our journey, we encountered time dilation. As speed increases, moving clocks appear to tick more slowly relative to stationary observers. The effect is tiny at highway speeds. It becomes measurable aboard satellites. Near the speed of light, it grows dramatic. According to the equations of special relativity, the time experienced by travelers continues decreasing as their velocity approaches the cosmic limit. If one were to extend those equations all the way to the speed of light itself, the factor describing time dilation would become infinite. From the perspective of an outside observer, the traveler's clock would appear to stop. No heartbeat, no ticking watch, no aging. Of course, this conclusion must be treated carefully. The equations are being pushed beyond the regime in which they describe a massive traveler. Since relativity already forbids such an object from reaching light speed, one cannot simply substitute that value into the equations and declare the result physically realized. Still, the trend is revealing. The closer matter comes to light speed, the more dramatically time behaves. It is as though space-time itself stretches the journey toward an unreachable boundary. Distance undergoes a similarly remarkable transformation. Length contraction causes distances measured along the direction of motion to become progressively shorter for the traveler. To observers on Earth, the nearest star beyond the Sun, Proxima Centauri, lies about 44 light-years away. At everyday speeds, that is an immense gulf. Even the fastest spacecraft humanity has launched would require tens of thousands of years to cover such a distance. But for travelers moving at a sufficiently high fraction of light speed, relativity predicts something extraordinary. The distance itself becomes shorter in their frame of reference. The star has not physically moved. Space has not folded. Rather, measurements of distance depend upon the observer's state of motion. As velocity increases, the gap between departure and destination contracts. This leads to one of the most beautiful insights in relativity. The universe does not prevent enormous journeys. It changes the meaning of distance and time during those journeys. A crew traveling at 99.9% of the speed of light could, in principle, experience a voyage lasting far less than the time measured by people remaining on Earth. Thousands of years might pass at home while only decades pass aboard the spacecraft. This does not violate relativity. Both descriptions are equally valid. The paradox disappears once one accepts that time itself is not universal. Yet none of this permits crossing the final boundary. The closer the spacecraft approaches light speed, the greater the required energy becomes. The equations continually push the destination farther away. The travelers may experience shorter journeys. They never actually arrive at the speed of light. Now suppose, purely as a logical exercise, that some unknown physics somehow allowed the barrier to be crossed. What would happen next? Here the thought experiment begins revealing why physicists take the light speed limit so seriously. According to special relativity, different observers disagree about the order of certain events separated by space. Normally, this disagreement never threatens causality because no signal can travel faster than light. The light cone preserves the order of cause and effect. But if faster than light travel became possible, some observers could calculate that a signal reached its destination before it had been sent. The exact details depend upon the relative motion of the observers, but the conclusion is robust. Events that appear perfectly sensible in one frame can become causally inverted in another. Imagine sending a message to a distant spacecraft. In one observer's calculations, the spacecraft receives the message before the transmitter on Earth has finished sending it. By combining multiple faster-than-light signals between observers moving relative to one another, it becomes possible, at least within the mathematics of special relativity, to construct situations in which information returns to its point of origin before it was originally transmitted. Physicists sometimes refer to such scenarios as causal loops. A message warns someone not to send the very message that produced the warning. The contradiction is immediately apparent. If the warning succeeds, the original message is never sent. If the original message is never sent, the warning cannot exist. These paradoxes are not merely entertaining puzzles. They suggest that the structure of space-time actively prevents such situations from arising. The light speed limit may therefore serve as a safeguard protecting the logical consistency of the universe. This possibility becomes even more intriguing when viewed alongside general relativity. Einstein's later theory describes gravity not as a force in the traditional sense, but as the curvature of space-time produced by mass and energy. Light follows this curved geometry. Planets follow it. Galaxies follow it. The speed of light is woven into the equations that determine how gravity itself behaves. If faster-than-light motion altered the ordering of cause and effect, it might also disrupt the very geometry upon which gravitation depends. Exactly how such a breakdown would occur remains unknown because no experimentally verified theory successfully unifies general relativity with quantum mechanics. That missing theory, often called quantum gravity, remains one of the greatest goals of modern physics, until it is discovered. Physicists cannot say with certainty what ultimately prevents every imaginable paradox. What they can say is that every successful theory tested so far points toward the same conclusion. Nature appears remarkably protective of causality. Curiously, this does not mean the universe lacks shortcuts. General relativity already allows phenomena that seem almost miraculous from an everyday perspective. The expansion of space carries distant galaxies away from one another faster than light without violating relativity because the galaxies are not racing through space faster than light. Instead, the space between them is stretching. Likewise, gravitational lensing bends the paths of light across enormous cosmic distances, allowing us to observe galaxies hidden behind others. The universe is capable of astonishing geometrical behavior. Yet none of these phenomena allow a human traveler to outrun light locally. The distinction is subtle but fundamental. Relativity does not forbid surprising journeys. It forbids locally exceeding the invariant speed that defines the structure of space-time. The thought experiment has therefore accomplished something unexpected. It has not shown how humanity might travel at the speed of light. Instead, it has revealed why such travel would ripple far beyond engineering. Time, distance, energy, causality, even the geometry of the cosmos, all appear to depend upon the same invisible boundary. And that realization raises an even larger question. If the speed of light is intertwined with so many different aspects of the universe, perhaps it is not merely one physical constant among many. Perhaps it is one of the organizing principles from which much of the cosmos itself emerges. At first, the speed of light appears to concern only one question. How fast can something travel? By now, however, the picture has become much richer. The same constant that governs beams of light and rapidly moving spacecraft has quietly appeared in discussions of time, distance, energy, momentum, causality, and the structure of space-time itself. This repetition is unlikely to be a coincidence. Throughout the history of physics, whenever the same idea continues to emerge in seemingly unrelated places, it often signals that something fundamental is being uncovered. The speed of light is one of those ideas. It is not simply a property of light. It is one of the organizing principles of the universe. One place where this becomes especially clear is gravity. Before Einstein, gravity was understood primarily through Isaac Newton's remarkable law of universal gravitation. Every mass attracted every other mass with a force that weakened with distance. The theory described planetary orbits with extraordinary accuracy and remained one of the greatest achievements in scientific history. Yet Newton's picture contained an unanswered question. How quickly does gravity act? If the Sun were somehow removed, would Earth instantly fly away from its orbit? Or would the change take time to reach us? Newton himself found the idea of instantaneous action across empty space deeply troubling. He admitted that he could not explain the mechanism responsible. Einstein's general theory of relativity offered a profoundly different picture. Instead of treating gravity as an invisible force acting across space, it described gravity as the geometry of spacetime itself. Mass and energy tell spacetime how to curve. Curved spacetime tells matter how to move. The Earth does not orbit the Sun because it is being pulled through space by an invisible rope. It follows the straightest possible path through curved spacetime, much as an aircraft follows the natural curvature of the Earth rather than flying through an invisible channel in the sky. This new description solved another important mystery. Changes in gravity do not travel instantly. They propagate at the speed of light. If the Sun's mass was somehow altered, Earth would not know immediately. the information would require about 8 minutes to arrive, because light itself takes about 8 minutes to travel from the Sun to our planet. Gravity, in Einstein's theory, respects the same universal speed limit. That prediction remained untested for nearly a century. Then, in 2015, humanity finally detected gravitational waves directly, these ripples in space-time, generated by merging black holes and neutron stars, moved across the cosmos at essentially the same speed as light. Exactly as general relativity predicted, a constant first introduced through the study of light turned out to govern gravity as well. The deeper physicists looked, the more universal the limit became. Black holes provide another remarkable illustration. A black hole is often described as an object from which not even light can escape. Although that statement is accurate, it is only part of the story. The true boundary surrounding a black hole is called the event horizon. Crossing this surface does not involve striking a physical wall. Instead, it marks a region where every future path through space-time leads inward, inside the horizon. Escaping would require traveling faster than light relative to the surrounding space-time geometry. Since relativity forbids this, escape becomes impossible. Notice what determines the boundary. Not enormous gravity crushing outward motion, not a mysterious barrier. The event horizon exists because the geometry of space-time itself has been distorted so dramatically that every possible path remaining below the speed of light leads deeper into the black hole. Once again, the light speed limit defines what the universe permits. The same relationship appears on vastly larger scales. Galaxies are not scattered randomly through space. They gather into clusters, filaments, and enormous cosmic webs stretching hundreds of millions of light-years across. The formation of these structures required information to travel. Tiny density fluctuations in the early universe gradually influenced surrounding matter through gravity. Yet those influences could never spread faster than the speed of light. As a result, there exists a maximum distance over which different regions of the universe could have affected one another during cosmic history. Cosmologists refer to related concepts as the observable universe and the cosmic horizon. There are regions so distant that light emitted there has not yet had enough time to reach Earth since the Big Bang. Those regions may exist. They may contain countless galaxies, but they remain beyond our current observational reach because the universe itself has a finite age, and light travels at a finite speed. In a profound sense, the speed of light determines not only how fast we can travel, it determines how much of the universe we are capable of seeing. The history of astronomy is therefore also a history of looking backward through time. When we observe the moon, we see it as it was about 1¼ seconds ago. The Sun appears as it existed roughly 8 minutes in the past. The Andromeda Galaxy is seen more than 2 million years ago. Some of the most distant galaxies visible with modern telescopes appear as they were over 13 billion years in the past, long before the Earth formed. Every telescope is therefore a time machine of a very particular kind. It cannot carry observers into the past. Instead, it allows ancient light to carry the past toward us. Without the finite speed of light, this extraordinary window into cosmic history would not exist. Stars themselves owe much of their behavior to the same principle. Deep within a star's core, nuclear fusion produces immense amounts of energy. That energy does not instantly emerge into space. Instead, photons scatter countless times while gradually making their way outward through dense stellar material. For our Sun, a photon created in the core may require tens of thousands, or even hundreds of thousands, of years before finally escaping from the visible surface. Only then does it begin the comparatively brief 8-minute journey to Earth. Even inside a single star, the finite speed of light shapes the movement of energy. This limitation influences how stars evolve, how they balance gravity against internal pressure, and how long they continue shining. Without it, stellar evolution would unfold in profoundly different ways. The speed of light also plays an essential role in one of the greatest discoveries of 20th century cosmology. In the late 1920s, Edwin Hubble found that distant galaxies generally appear to be moving away from us. The farther the galaxy, the greater its recession speed. This observation revealed that the universe itself is expanding. Today we understand that galaxies are not simply flying through pre-existing empty space. Rather, the space between them is stretching. Here an important distinction emerges. Special relativity forbids objects from moving locally through spacetime faster than light. General relativity allows spacetime itself to expand. At sufficiently great distances, this expansion can cause galaxies to recede from one another at effective speeds exceeding the speed of light without violating relativity. No galaxy is breaking the cosmic speed limit within its local region. Instead, the ruler used to measure the distance is itself changing. This subtle difference often causes confusion, but it beautifully illustrates how deeply the speed of light is tied to geometry rather than merely motion. The constant appears again in Einstein's famous field equations, in Maxwell's equations, in quantum electrodynamics, in the propagation of gravitational waves, and in the causal structure governing every physical interaction we have yet observed. It is woven into nearly every successful description of the natural world. The more connections we uncover, the less the speed of light resembles an isolated physical quantity. Instead, it begins to look like one of the universe's fundamental threads, binding together phenomena that once seemed entirely unrelated. Yet another surprise awaits. As physicists push deeper into the microscopic world, studying atoms, electrons, and quantum fields, they discovered that many of the same constants and principles governing stars and galaxies also appear inside the smallest building blocks of matter. The greatest mysteries of the very large and the very small were beginning to converge, and at their intersection, the speed of light would once again occupy the center of the story. One of the most beautiful moments in science arrives when two seemingly unrelated ideas suddenly reveal themselves to be parts of the same story. For centuries, the study of the heavens and the study of the atom appeared to belong to different worlds. Astronomers measured the motions of planets, stars, and galaxies across unimaginable distances. Physicists examined the behavior of electrons, atoms, and radiation on scales far too small to see. The question seemed completely different. One explored the largest structures in existence, the other explored the smallest. Yet throughout the 20th century, these two paths slowly curved toward one another. At their meeting point stood the same constant that had guided our journey from the beginning: the speed of light. This convergence first became apparent through the development of quantum mechanics. While Einstein was reshaping our understanding of space-time, other physicists were discovering that matter behaved in unexpectedly wave-like ways. Electrons, once imagined as tiny solid particles orbiting atomic nuclei like miniature planets, displayed interference patterns normally associated with waves. Light, long understood as a wave through Maxwell's equations, also behaved like a stream of discrete particles called photons. The comfortable distinction between particles and waves began to dissolve. Nature seemed to speak a language unlike anything encountered in everyday life. Eventually, these discoveries evolved into quantum field theory, one of the most successful scientific frameworks ever developed. According to this picture, the universe is permeated by fundamental fields extending throughout all of space. There is an electron field, a photon field, fields associated with quarks, neutrinos, and many other particles. What we call a particle is not a tiny independent object traveling through an empty void. Instead, it is a localized excitation of its corresponding field. A photon is an excitation of the electromagnetic field. An electron is an excitation of the electron field. Even what appears to be empty space contains these fields everywhere. This idea changes the meaning of emptiness itself. If every point in the universe is occupied by quantum fields, then the vacuum is not an absence of reality. It is the lowest energy state of an extraordinarily rich physical structure. Even when no particles are present, the fields remain. They fluctuate. They interact. They possess measurable properties. This realization creates an unexpected bridge to our earlier discussion. Maxwell's equations determine the speed of electromagnetic waves through the electrical and magnetic properties of empty space. Quantum field theory tells us that empty space itself possesses structure. Perhaps these two insights are connected. Perhaps the speed of light is not simply imposed upon the vacuum. Perhaps it emerges naturally from the vacuum's most fundamental properties. Physicists continue investigating exactly this possibility. At present, quantum electrodynamics, the quantum theory describing light and electromagnetism, predicts experimental results with extraordinary accuracy. Some calculations agree with laboratory measurements to more than 10 decimal places. Few scientific theories have ever achieved such precision, yet even this remarkable success leaves deeper questions unanswered. Quantum mechanics describes matter and radiation with astonishing effectiveness. General relativity describes gravity and spacetime with equal elegance. Each theory has survived every experimental test within its domain. The difficulty arises when physicists attempt to combine them. Black holes illustrate the problem beautifully. Far from their centers, general relativity provides an excellent description. The curvature of spacetime explains the motions of stars orbiting the black hole, the paths of light bending around it, and the gravitational waves emitted when black holes merge, but near the central singularity predicted by classical relativity. Densities become so extreme that quantum effects can no longer be ignored. The mathematics of general relativity predicts infinities. Quantum mechanics, meanwhile, was never designed to describe spacetime itself as a dynamic entity. Each theory reaches beyond the region where it comfortably applies. Something deeper seems to be missing. The same difficulty appears when cosmologists look backward toward the earliest moments of the universe. General relativity successfully describes cosmic expansion once the universe has grown beyond its earliest instance. Quantum physics successfully explains the behavior of fundamental particles, but during the first tiny fraction of a second after the Big Bang, both descriptions become essential simultaneously, without a complete theory of quantum gravity. Scientists cannot yet describe that era with full confidence. This is not a failure of either theory. It is a sign that both may emerge from an even deeper framework. Once again, the speed of light occupies a central role. It appears in Einstein's equations. It appears in quantum electrodynamics. It defines causal relationships. It connects energy with mass through EEMs2. It links electric and magnetic fields. It governs the propagation of information. Any successful unification of modern physics must preserve or explain all of these relationships. Few constants play such an extensive role. Another surprising connection involves the Higgs field. For much of the 20th century, physicists understood that elementary particles possessed mass, but they lacked a satisfying explanation for why. Then came the development of what is now called the Standard Model of Particle Physics. Within this framework, particles interact with an all-pervading Higgs field. Those interactions give many fundamental particles their mass. The experimental discovery of the Higgs boson at the Large Hadron Collider in 2012 confirmed a crucial part of this picture. Here another remarkable relationship emerges. Photons do not interact with the Higgs field in the same way that electrons and quarks do. Consequently, photons remain massless, and because they are massless, they travel at the invariant speed of light. Matter, by contrast, acquires mass through its interactions with the Higgs field. That mass places matter inside the light cone rather than upon its boundary. This does not fully explain why the speed of light has its particular value, but it reveals another hidden connection. The distinction between light and matter is tied to one of the deepest mechanisms known in particle physics. The story becomes even richer when considering neutrinos. These elusive particles interact only weakly with ordinary matter and possess extremely small masses. For many years, physicists believed neutrinos were completely massless. If that had been true, they would travel exactly at the speed of light. Experiments eventually revealed that neutrinos do possess tiny but non-zero masses. As a result, they travel incredibly close to the speed of light, but not exactly at it. The difference is extraordinarily small, yet it beautifully reinforces the broader pattern. Massless particles move at the invariant speed. Particles with mass remain below it. Nature appears remarkably consistent. The convergence continues in cosmology. The cosmic microwave background, the faint afterglow of the early universe, carries information that has travelled for nearly the entire age of the cosmos. Tiny fluctuations within that ancient radiation reveal how matter was distributed when the universe was only about 380,000 years old. From those subtle variations grew every galaxy, every star, every planet, and eventually every living observer. Yet the growth of those structures was constrained from the beginning by causal horizons determined by the speed of light. Regions too far apart could not exchange information. Gravity, radiation, and matter evolved within boundaries established by space-time itself. The larger structures in the observable universe therefore carry the imprint of the same speed limit governing photons in a laboratory. The infinitely large and the unimaginably small continue to tell the same story. As these connections accumulated over the past century, physicists began to suspect that many of the separate laws appearing in textbooks are different expressions of a smaller set of underlying principles: electricity, magnetism, light, mass, energy, space-time, quantum fields, gravity. None now appear entirely independent. Instead, they resemble threads woven into a single tapestry whose complete pattern has not yet been fully revealed. That realization has profoundly shaped modern research. Today's observatories no longer study stars alone. Particle accelerators no longer investigate only subatomic particles. Gravitational wave detectors, space telescopes, neutrino observatories, and enormous computer simulations all contribute pieces to the same puzzle. Humanity has begun exploring the universe with an unprecedented collection of tools. Each offers a different window onto the same enduring mystery. And each new observation, while answering old questions, seems to uncover even deeper ones. If Galileo could step into a modern observatory, he might first notice how quiet it is. There are no towering brass instruments turned by hand, no observers sketching planets by candlelight, no endless nights spent estimating positions against the stars. Instead, there are computers processing unimaginable quantities of data, detectors cooled to temperatures only a fraction of a degree above absolute zero, mirrors polished so precisely that their imperfections are measured in atoms, and antennas spread across continents, working together as though they were a single instrument the size of Earth itself. The questions, however, remain remarkably familiar. How does the universe work? Why does it behave as it does? And is there anything beyond the limits we currently understand? Modern astronomy has not abandoned Einstein's ideas. Quite the opposite. It has spent decades placing them under increasingly demanding tests. Every new telescope, every particle detector, and every spacecraft becomes another opportunity to discover where relativity succeeds, where it might require refinement, and whether the cosmic speed limit is truly absolute. One of the greatest advances has come from observing the universe across the entire electromagnetic spectrum. Human eyes detect only a narrow band of visible light, but the cosmos shines in radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. Each wavelength reveals different physical processes. Radio telescopes trace enormous clouds of hydrogen stretching between galaxies. Infrared observatories peer through dust to witness newborn stars emerging inside dense molecular clouds. X-ray telescopes reveal matter spiraling toward black holes at temperatures of millions of degrees. Gamma-ray observatories detect the most energetic explosions known in nature. Despite their enormous differences, every one of these forms of electromagnetic radiation travels through the vacuum at the same invariant speed, whether a photon carries the gentle warmth of infrared light or the immense energy of a gamma ray. Relativity predicts that its speed remains unchanged in empty space. Astronomers have tested this prediction using some of the most violent events ever observed. Gamma ray bursts, brief flashes produced by collapsing massive stars or merging neutron stars, release more energy in seconds than our sun will emit during its entire lifetime. Their light often travels billions of years before reaching Earth. If photons of different energies moved at slightly different speeds, those tiny differences would accumulate over such extraordinary distances. The highest energy photons would arrive noticeably earlier or later than lower energy ones. Modern observatories have searched carefully for exactly this effect. Within the limits of current measurements, the arrival times remain consistent with a single universal speed. Once again, Einstein's prediction survives. Space itself appears remarkably impartial. Another powerful tool comes from gravitational wave astronomy. The first direct detection in 2015 opened an entirely new way of studying the cosmos. Unlike light, which can be blocked, absorbed, or scattered by matter, gravitational waves travel almost unhindered across the universe. They carry information directly from some of the most extreme events imaginable. Each detection provides another opportunity to compare the behavior of gravity with the predictions of general relativity. The 2017 observation of merging neutron stars proved especially valuable because astronomers detected both gravitational waves and electromagnetic radiation from the same event. The nearly simultaneous arrival of these signals, after travelling approximately 130 million light-years, placed extraordinarily strong limits on any difference between their propagation speeds. If gravity behaved even slightly differently over such enormous distances, the discrepancy would likely have become visible. Instead, the agreement reinforced one of relativity's central ideas. The same cosmic structure governs both light and gravity. Meanwhile, particle physics continues pushing matter closer to the light speed limit than ever before. The Large Hadron Collider accelerates protons to energies of several tera-electron volts before bringing them into collision. The purpose is not to make particles exceed light speed. It is to recreate conditions resembling those that existed fractions of a second after the Big Bang. Each collision briefly produces particles that no longer exist naturally under ordinary conditions. By studying these particles, physicists test the standard model with extraordinary precision while searching for subtle deviations that might hint at new physics. So far, the standard model has proven remarkably resilient. The discovery of the Higgs boson in 2012 confirmed one of its final missing components. Yet many questions remain. Dark matter has never been directly detected. Dark energy, responsible for the accelerating expansion of the universe, remains deeply mysterious. Neither phenomenon is fully explained within the standard model. Some physicists hope that future particle experiments may reveal entirely new particles or interactions connected to these cosmic puzzles. Whether such discoveries would alter our understanding of the speed of light remains unknown. Another frontier lies in the study of black holes. For decades, black holes were inferred indirectly through the motions of nearby stars and the radiation emitted by falling matter. Then, in 2019, the Event Horizon Telescope released the first image of the shadow surrounding a supermassive black hole, rather than relying on a single telescope. The project linked radio observatories across Earth using a technique known as very long baseline interferometry. Together, they effectively created a telescope nearly the size of our planet. The resulting image beautifully matched the predictions of general relativity. The size of the shadow, the surrounding ring of emission, and the overall geometry agreed closely with theoretical expectations. In 2022, the collaboration followed this achievement with an image of the black hole at the center of our own Milky Way. Again, Einstein's theory passed another demanding observational test. Space-based observatories have transformed cosmology in similar ways. The Hubble Space Telescope measured the expansion of the universe with unprecedented precision and revealed galaxies from the distant past. The Planck spacecraft mapped tiny temperature variations in the cosmic microwave background, providing one of the most detailed pictures ever obtained of the early universe. More recently, the James Webb Space Telescope has extended humanity's vision even farther, observing galaxies that formed only a few 100 million years after the Big Bang. These observations are reshaping our understanding of how the earliest stars and galaxies assembled. Some discoveries have surprised astronomers by revealing unexpectedly mature galaxies in the young universe. Whether these findings require new physics or simply refinements to existing models remains an active area of research. The observations are exciting not because they overturn relativity, but because they challenge details of cosmic evolution while leaving the broader framework intact. Computer simulations have become another indispensable scientific instrument. Modern supercomputers model galaxy formation, black hole mergers, stellar explosions, and the evolution of cosmic structure across billions of years. These simulations incorporate the known laws of gravity, electromagnetism, nuclear physics, and fluid dynamics. When their predictions agree with observations, confidence in the underlying theories grows. When discrepancies appear, researchers investigate whether the problem lies in missing physics, incomplete data, or limitations of the simulations themselves. Increasingly, progress comes not from isolated discoveries but from combining many independent lines of evidence. Neutrino observatories buried beneath ice or deep underground detect particles that pass almost effortlessly through entire planets. Radio arrays map hydrogen across enormous regions of the sky. Spacecraft measure subtle gravitational effects within our own solar system. Atomic clocks become ever more precise, allowing increasingly sensitive tests of relativity. Each experiment narrows the space in which new physics might hide, and yet that remaining space has not disappeared. In fact, some of the most important modern research focuses precisely on the smallest possible deviations from Einstein's predictions. If quantum gravity slightly modifies space-time at the Planck scale, the effects would likely be almost unimaginably tiny. Only the most precise measurements across the greatest cosmic distances might reveal them. For this reason, astronomers continue monitoring gamma-ray bursts, pulsars, fast radio bursts, gravitational waves, and the motions of stars orbiting supermassive black holes. Each observation serves as another careful question posed to the universe. Do the laws we know remain exact under every condition, or is there a deeper layer waiting just beyond the reach of our current instruments? So far, nature has answered with remarkable consistency. Relativity continues to describe the observations with extraordinary success, but science is never satisfied merely because a theory has survived many tests. Every successful theory invites even more demanding questions. Every improved instrument reaches farther than the last. And every new discovery reminds us that confirmation is not the end of curiosity. It is the beginning of more careful investigation. For despite everything modern astronomy has revealed, some of the most profound questions remain exactly where they were when our journey began. Not because scientists have failed, but because the universe still guards some of its deepest secrets. There is a quiet humility that runs through the history of science. Each generation has believed it stood close to a complete understanding of the universe, only to discover that a deeper layer remained hidden beneath the one it had just uncovered. Isaac Newton revealed that the motions of apples and planets obey the same mathematical laws. Then Maxwell showed that electricity, magnetism, and light were different expressions of a single phenomenon. Einstein reshaped space and time into one continuous fabric. Quantum mechanics uncovered a microscopic world governed by probabilities rather than certainties. Each breakthrough solved problems that had puzzled earlier generations. Each also created entirely new mysteries. Today, despite the extraordinary success of modern physics, scientists once again find themselves standing at such a frontier. The speed of light has survived every experimental challenge so far. Relativity has explained observations ranging from the behavior of atomic clocks to the motions of galaxies. Yet explaining how a rule operates is not always the same as explaining why it exists. That distinction marks the beginning of uncertainty. One of the deepest unanswered questions concerns the nature of space-time itself. General relativity treats space-time as a smooth, continuous geometry, whether describing the orbit of Earth or the collision of two black holes. The theory assumes that space-time can be divided into ever smaller distances without limit. Quantum physics suggests that nature may not behave so simply. At sufficiently tiny scales, perhaps around the Planck length of roughly 1.661035 meters, many physicists suspect that the familiar picture of smooth space-time may no longer apply. This scale is almost unimaginably small. If a single atom were enlarged to the size of the observable universe, the Planck length would still remain smaller than the enlarged atom. No existing microscope can approach it. No particle accelerator can probe it directly. Whether space-time remains continuous or possesses some deeper microscopic structure is unknown. This uncertainty matters because the speed of light is defined within space-time itself. If space-time has a more fundamental architecture, perhaps the origin of the light speed limit is hidden there, or perhaps the limit survives unchanged even at those extreme scales. At present, no experiment can distinguish between these possibilities. Quantum gravity remains another great unknown. General relativity describes gravity as geometry. Quantum mechanics describes nature through quantum fields and probabilities. Each framework is extraordinarily successful within its own domain, yet no complete theory has successfully unified them while remaining experimentally verified. Several candidates have been proposed. String theory suggests that the fundamental constituents of reality are tiny vibrating strings existing in additional spatial dimensions. Loop quantum gravity explores the possibility that space-time itself is built from discrete quantum units, Other approaches investigate emergent spacetime, causal sets, asymptotic safety, and still more speculative ideas. Each offers intriguing mathematical insights. None has yet received decisive experimental confirmation. Physicists therefore remain careful. These are active areas of research, not established descriptions of reality. Dark matter introduces another profound uncertainty. Astronomers observe galaxies rotating too rapidly for their visible matter alone to account for the gravitational effects. Clusters of galaxies bend light more strongly than ordinary matter appears capable of producing. The cosmic microwave background carries signatures pointing toward additional unseen mass. Together, these observations strongly support the existence of dark matter, yet no one knows its true identity, despite decades of increasingly sensitive experiments. The particles responsible have not been directly detected. Could dark matter interact with space-time in ways that subtly illuminate the origin of the speed of light? Perhaps, or perhaps the two mysteries are entirely unrelated. At present, science cannot answer. Dark energy presents an equally remarkable puzzle. Near the end of the 20th century, observations of distant supernovae revealed that the expansion of the universe is accelerating. Some form of energy associated with empty space appears to dominate the large-scale evolution of the cosmos. Physicists call it dark energy, because they observe its gravitational effects while remaining uncertain about its underlying nature. It represents roughly 70% of the total energy content of the observable universe. Yet its origin remains one of the greatest unsolved problems in cosmology. The vacuum itself appears to possess energy, but calculations from quantum field theory predict values enormously larger than those inferred from astronomical observations. Reconciling these two descriptions has proven extraordinarily difficult. If empty space determines both the speed of light and the large-scale expansion of the universe, perhaps deeper connections remain hidden. No evidence has yet revealed what those connections might be. Even constants that seem perfectly fixed continue to be tested. The speed of light in a vacuum is treated as constant throughout modern physics. Indeed, it is now built directly into the International System of Units by defining the meter in terms of the distance light travels in a specified fraction of a second. Nevertheless, astronomers continue searching for any sign that fundamental constants may have changed over cosmic history. By studying light from distant quasars and ancient galaxies, researchers compare atomic spectra across billions of years. Thus far, observations remain consistent with a constant speed of light and stable physical laws. But the search continues because even an extraordinarily tiny variation would reshape our understanding of the universe. Another uncertainty lies in the limits of observation itself. Much of the observable universe will forever remain inaccessible to direct exploration. The cosmic expansion ensures that some galaxies are already receding in such a way that light emitted today will never reach us. Beyond the observable horizon may exist regions governed by exactly the same physical laws, or there may be features we cannot presently imagine. Science is careful here. The observable universe is not necessarily the entire universe. It is simply the portion from which information has had time to arrive. Everything beyond that boundary remains observationally uncertain. Technology also imposes practical limits. The Large Hadron Collider represents one of humanity's greatest engineering achievements, yet its energies remain unimaginably smaller than those naturally present during the earliest moments after the Big Bang. Gravitational wave observatories detect astonishingly subtle distortions in space-time, but still observe only certain kinds of cosmic events. Even the James Webb Space Telescope, capable of seeing galaxies from the dawn of cosmic history, cannot peer all the way back to the Big Bang itself. Every instrument has a horizon beyond which it cannot currently reach. Future generations will almost certainly build better ones, but every advance reveals new questions alongside new answers. Perhaps the most important uncertainty is philosophical rather than technical. How should scientists respond when evidence runs out? The scientific method offers a remarkably disciplined answer. Where observations exist, follow them. Where measurements end, distinguish clearly between theory, hypothesis, and speculation. Do not confuse mathematical possibility with physical reality. Do not mistake unanswered questions for evidence of extraordinary conclusions. This discipline is one reason modern physics has become so reliable. It embraces uncertainty without surrendering to guesswork. In many ways, Uncertainty is not a weakness. It is the engine of discovery. If every question had already been answered, there would be no reason to build larger telescopes, more sensitive detectors, or more powerful particle accelerators. There would be no reason to continue exploring the heavens. Instead, every unanswered question serves as an invitation. Not an invitation to believe whatever we wish, an invitation to look more carefully. The closer humanity approaches the edge of knowledge, the more apparent it becomes that understanding the speed of light may ultimately require understanding reality itself. And that is a journey that has only just begun. Every scientific frontier has a curious appearance. From a distance, it often looks like the edge of knowledge itself, yet when researchers finally arrive there, they discover not a wall, but another horizon waiting beyond it. The questions have changed, the tools have improved, and the answers have become more precise. But the boundary continues to move. Today, the speed of light sits at one of those horizons. It is among the most carefully tested principles in all of physics. And yet it is also one of the deepest clues that our understanding of reality remains incomplete. Einstein's theories have survived more than a century of increasingly demanding experiments. Every new observation has strengthened confidence that special and general relativity describe nature with extraordinary accuracy. But no physicist believes that science has reached its final chapter. History offers too many reminders that every successful theory eventually reveals a domain where something deeper must take over. Newton's mechanics remains indispensable for launching satellites, designing bridges, and predicting the motions of planets. Yet at very high speeds, and in very strong gravitational fields, relativity provides a more complete description. Likewise, relativity itself may someday be recognized as part of a broader framework that includes quantum gravity. If such a theory exists, where might scientists find the first evidence? One possibility lies near black holes. Black holes already represent the most extreme gravitational environments known in the observable universe. Near their event horizons, gravity bends space-time so dramatically that light itself follows curved paths around them. At their centers, according to classical general relativity, lies a singularity where the equations predict infinite density and infinite curvature. Most physicists suspect that these infinities signal the limits of the theory, rather than the existence of physical infinities in nature. Some new description must eventually replace them, but reaching that description is extraordinarily difficult. The event horizon hides the central region from direct observation. No spacecraft can enter, collect measurements, and return. Instead, astronomers must study the behavior of matter, light, and gravity surrounding black holes, hoping that subtle clues reveal what occurs deeper inside. Future observatories promise to sharpen this picture. Next-generation gravitational wave detectors such as the planned space-based laser interferometer, space antenna, often called LISA, are expected to observe mergers involving supermassive black holes across much of cosmic history. These signals may allow physicists to test general relativity with unprecedented precision. Tiny discrepancies between observation and prediction could hint at new physics operating where gravity becomes strongest. Another frontier stretches back toward the earliest moments of cosmic history. The first fraction of a second after the Big Bang remains hidden behind conditions too energetic for existing theories to describe completely. During that era, gravity, quantum physics, and the other fundamental interactions may have behaved very differently from the way they do today, if traces of those conditions remain imprinted in the universe. Future observations of the cosmic microwave background or primordial gravitational waves might reveal them. Detecting such signals would be one of the greatest achievements in the history of astronomy. It would allow humanity to investigate a time long before the first stars existed. Particle physics offers another path. The Large Hadron Collider has already transformed our understanding of fundamental particles, but physicists are planning even more powerful accelerators capable of reaching higher energies and greater precision. These machines are not built simply to search for new particles. They are designed to explore where existing theories may begin to fail. A tiny deviation from the standard model, a previously unknown particle, or an unexpected interaction could illuminate questions extending far beyond particle physics itself. Perhaps the origin of mass, the nature of dark matter, or the structure of space-time will become a little clearer, or perhaps nature will surprise us in ways no one currently anticipates. Astronomy is entering a similarly remarkable era. The Vera C. Rubin Observatory is expected to survey the southern sky repeatedly, creating an unprecedented record of changing cosmic events. The square-kilometre array will become the largest radio telescope ever constructed, mapping hydrogen across enormous regions of the universe and probing cosmic evolution with extraordinary sensitivity. Future space telescopes may directly observe Earth-like planets orbiting distant stars while simultaneously extending our view toward galaxies even closer to the dawn of cosmic history. Each new instrument expands humanity's senses. Each allows us to ask questions that previous generations could scarcely formulate. Yet even these extraordinary observatories cannot solve every mystery. Some limits arise not from technology but from nature itself. The observable universe has a finite horizon because light has travelled for only a finite time since the Big Bang. No telescope, regardless of size, can directly observe regions from which light has not yet had time to arrive. Likewise, quantum uncertainty is not merely a limitation of measurement. It appears to be built into the behaviour of microscopic systems themselves. Recognizing these natural boundaries is an important part of scientific maturity. Progress does not require believing that every mystery will eventually disappear. Some questions may remain inaccessible for generations. Others may prove fundamentally unanswerable through direct observation. Science advances by learning to distinguish between those possibilities rather than assuming one or the other. This perspective also reshapes the meaning of the speed of light. At the beginning of our journey, it appeared to be a barrier preventing faster travel. Now it seems more like a cornerstone supporting an entire structure. It determines how information moves. It preserves the order of cause and effect. It links mass with energy. It shapes the behavior of gravity. It governs the evolution of stars and galaxies. It defines the observable limits of the cosmos. Whether a future theory ultimately explains the speed of light more deeply, or reveals an even richer framework beneath it. That theory must also explain why relativity has worked so well for so long. Any new understanding must contain Einstein's insights in the same way that relativity contains Newton's. Science rarely discards successful ideas. It places them within broader ones. This is why physicists remain both confident and cautious. Confident because the evidence supporting relativity is overwhelming. Cautious because history teaches that even the strongest theories may represent approximations to deeper truths. Some researchers wonder whether spacetime itself could emerge from quantum information. Others investigate whether gravity is an emergent phenomenon rather than a fundamental interaction. Still others search for subtle quantum structures hidden beneath the smooth geometry described by general relativity. These ideas differ dramatically from one another. What unites them is their commitment to the same scientific method that guided Einstein more than a century ago. Begin with evidence. Construct mathematical descriptions. Test every prediction. Accept only what nature confirms. The frontier therefore remains open, not because relativity has failed, but because success has revealed questions that only an even deeper understanding can answer. Somewhere beyond today's theories may lie the explanation for why spacetime possesses the properties it does, why the vacuum has the structure it has, why the constants of nature take the values they do, and why the speed of light has become one of the defining features of reality itself. Whether humanity will discover those answers in the coming decades or centuries is impossible to know. What is certain is that the search will continue. Every new telescope, every detector, every spacecraft, and every careful calculation carries us a little farther toward the boundary between what is known and what still waits beyond our reach. Beyond that boundary lies not certainty, but possibility. And it is there, at the edge of knowledge, that science is most alive. At the beginning of this journey, it seemed natural to think of the speed of light as a destination. A remarkable one, certainly, but still a destination. If human ingenuity could continue advancing for long enough, perhaps one day we would build engines powerful enough to cross that final threshold. The challenge appeared to be one of engineering, patience, and imagination. The universe has gently led us toward a different understanding. The speed of light is not simply a milestone waiting farther down the road. It is part of the road itself, as our understanding deepened. The familiar picture slowly gave way to something far more subtle. A beam of light was no longer just illumination crossing empty space. It became a clue to the architecture of reality. A spacecraft accelerating through the darkness was no longer simply moving from one place to another. It was tracing a path through space-time, where distance, time, energy, and motion are woven together far more intimately than everyday experience suggests. Perhaps this is one of the quiet gifts of astronomy. The night sky invites us to ask questions that first appear practical, only to discover that they are philosophical in the deepest scientific sense. How fast can we travel becomes, what is space? What is time? What does it mean for one event to cause another? Long before humanity built telescopes, people looked upward and wondered whether the stars might someday be reached. Today we know that many of those stars are accompanied by planets. Some almost certainly possess oceans. Others may have thick atmospheres, frozen landscapes, or skies illuminated by multiple suns. Across the Milky Way alone, there may be hundreds of billions of worlds. The dream of visiting them has lost none of its power. If anything, modern astronomy has made the dream even richer. Yet it has also revealed the extraordinary scale of the cosmos. Light itself requires more than 4 years to travel from Earth to the nearest star beyond the Sun. To cross the Milky Way from one side to the other, light would need roughly 100,000 years. Between galaxies lie distances so immense that ordinary language begins to lose its usefulness. Numbers become too large to picture. Comparisons become too small to matter. The universe quietly reminds us that it was never designed around human scales. And yet, despite those overwhelming distances, we are not entirely separated from the cosmos. Every photon entering a telescope has completed a journey that may have begun millions or billions of years ago. Every observation is an encounter with ancient history. The atoms within our bodies were forged inside stars that lived and died long before the Earth existed. The calcium in our bones, the oxygen we breathe, the iron carried by our blood all emerged from stellar furnaces scattered across the galaxy. In a very literal sense, the universe has already reached us, long before we ever dreamed of reaching it. That realization gently changes the meaning of exploration. Travel is only one way of knowing the cosmos. Observation is another. Understanding is another still. Humanity has crossed astonishing distances without leaving its own planet, by learning how light behaves. We have measured galaxies whose light began travelling toward us before the solar system formed, by studying subtle fluctuations in the cosmic microwave background. We have reconstructed conditions that existed when the universe itself was only a few 100,000 years old. Through gravitational waves, we have listened to black holes merging more than 1 billion years in the past. None of these achievements required outrunning light. They required learning how to read the messages that light and gravity patiently carry across the universe. There is something quietly beautiful in that thought. The greatest discoveries often come not from overcoming nature's limits, but from understanding why those limits exist. Again and again, science has revealed that boundaries are not always obstacles. Sometimes they are signposts. The horizon limits how far we can see because the Earth is curved. The event horizon of a black hole marks a profound feature of space-time. The speed of light defines the causal structure through which the universe unfolds. Each limit teaches us something about the deeper geometry of reality. That perspective also reshapes our relationship with uncertainty. Throughout this documentary, we have carefully distinguished between observation, theory, hypothesis, and speculation. Some questions have well-tested answers. Others remain open. We know that no object with mass has ever been observed reaching the speed of light. We know that relativity has been confirmed with extraordinary precision. We know that modern technologies, from satellite navigation to particle accelerators, quietly depend upon its predictions every day. But we also know that important mysteries remain. We do not yet possess a complete theory uniting quantum mechanics with gravity. We do not know the true nature of dark matter. We do not understand why dark energy appears to dominate the expansion of the universe. We cannot yet say whether spacetime itself is fundamentally continuous or whether it emerges from an even deeper quantum structure. Those uncertainties are not signs of failure. They are evidence that science remains alive. Every generation inherits both answers and questions. The answers become the foundation upon which new questions are built. The questions become invitations rather than disappointments. This rhythm has guided astronomy since the first people looked upward with nothing more than their eyes. It continues today through telescopes orbiting Earth, observatories spread across mountain peaks, detectors listening for gravitational waves, and particle accelerators probing the smallest known scales of nature. Perhaps future scientists will discover principles that today remain completely beyond our imagination. Perhaps they will explain why the speed of light possesses exactly its measured value. Perhaps they will uncover a deeper description from which space-time itself emerges. Or perhaps they will find that Einstein's insight, like Newton's before it, is part of a still larger story whose outlines are only beginning to appear. Whatever those discoveries may be, they will almost certainly preserve one lesson that has echoed throughout our journey. The universe is rarely simpler than our first intuition. It is often more elegant. The dream of travelling at the speed of light may never become reality for beings made of ordinary matter. Yet in pursuing that dream, humanity uncovered something even more remarkable. We discovered that the limit was never merely about speed. It was a window into the hidden order of the cosmos. And so we return, quietly, to the question that first set us on this path. If the speed of light is not simply the fastest that anything can move, but one of the fundamental threads from which space, time, gravity, and causality are woven, what deeper pattern might still lie beneath it, waiting for some future generation to discover?